This is Lab 2, Motion of a Falling Object. For my experiment, I dropped a crumbled piece of aluminum foil from a height similar to my own, following the negative y-axis. As the foil fell, acceleration occurred due to drag and gravity, which I captured in 19 frames. Based on Newton's second law and the momentum principle, we discovered that if the net force is not equal to zero, then the object will have an acceleration and change in momentum. As shown, I dropped the foil in the negative y direction, but I did not throw it. Simply dropping the object allowed for only the force of the earth, gravity, and drag force to apply. If I had thrown it down, another force, my own, would also be applied to the object, increasing the net force, and therefore increasing the terminal velocity. The graph illustrates the velocity of the foil, which starts at zero and then quickly increases due to acceleration. The foil is able to accelerate downward because the opposing force to gravity, drag, is smaller than the force of gravity, pulling the foil to the earth. In addition to the video analysis, a Python file was created to model and predict the position of the foil at each time interval. This program greatly helps us to understand Newton's second law and the momentum principle. We know that in order to have an acceleration and change in momentum, the net force applied to the object must be non-zero. In the code, we must first set our initial position and velocity and the mass of the object. We must also include the gravity constant, 9.8 meters per second squared, the direction in which the foil is traveling, and the magnitude of the drag force. In order to obtain a more correct model, we must make sure net force incorporates both drag force and gravity. Gravity is equal to the mass of the object times the gravity constant, 9.8 meters per second. Drag is equal to the drag constant, commonly referred to as b, times velocity squared. This shows the important relationship between force and velocity, that if you needed a changing velocity, non-zero forces must be applied. When the net force is calculated, you should see that force of gravity is greater than drag, and so the object accelerates downward. Using the computer models, I was able to graph the position versus time comparing the experiment's data to the model's predictions. However, two separate models were created, one incorporating drag force and gravity, and one with only gravity incorporated. As predicted, the model including both forces more realistically was the better fit. Both curves have a negative slope showing the effects of gravity accelerating the object down. When the model includes both forces, the terminal velocity matches what appears perfectly, thanks to a correctly identified b constant, or drag force magnitude. There is only one discrepancy in the middle of the curves where the model underpredicts slightly. This may be because the model predicts the drag force to be a little greater than actually is, or human error with plotting may have occurred. The second plot is that with only gravity included, and a large difference between curves occurs because of this. The model overpredicts by quite a bit due to no opposing forces, the drag force not existing in this model. So the object accelerates more, creating a larger terminal velocity in the model than actually occurred. This effect is similar to if the foil had been thrown down, since the force applied downward would be greater. This curve would look more like the model not including drag with a larger terminal velocity. In the end, we discovered that by calculating all forces applied to an object, we can predict its motion. If the net force is non-zero, we have an acceleration, and therefore changing momentum and velocity.